Namaste everyone. Welcome to our last class on mechanical properties of solids. Today's class will be a short class where we will be winding up the lesson with discussion on some more elastic effects and some of the major applications of elasticity of materials. So what are the other elastic effects that we are going to see? As you see on our boards, we are going to see three effects. One is elastic after effect, elastic fatigue, and elastic hysteresis. Now, what is meant by elastic after effect? Now, in some of the cases, like a rubber band, when you stretch a rubber band and remove the deforming forces, the body is going to regain its original shape immediately. Immediately, isn't it? But there are certain cases where there will be a delay in the body in regaining its original shape. So the delay in regaining its original shape, right? The delay that the body has in regaining its original shape on the removal of the deforming forces is called elastic after effect, right? There may be cases where you bend it. When you bend an object, when you leave it, it will immediately come back to its original shape. Some of them, they may not come immediately, but left alone, maybe after a few minutes, after a few hours, or after even a day, depending on the material, they will regain, but the time duration in which they will regain will differ. So that delay that is caused in regaining its original shape, right? The delay in regaining the original shape of a body on removing the deforming force is what we call as elastic after effects. Now, where do we see this? In electrical instruments like galvanometers, we have a very sensitive spring. The suspension is made up of the pointer rests on phosphor bronze alloy, a spring that is made up of phosphor bronze alloy spring. The spring is going to be made up of phosphor bronze alloy spring, which has a very small elastic after effect. So that means, what is the meaning of that small elastic after effect? Money, it will immediately regain its shape on removal of the deforming force. So when the current stops, the galvanometer just comes back to zero. It is not going to come back slowly. It is not going to retrace slowly. You would have seen this in your physics labs, where the moment the contact with the or the current is removed, the galvanometer comes back with a, we call it as deadbeat of the galvanometer, comes immediately to zero. So in which case the elastic after effect is very small. Whereas in the case of certain glass fibers, in the case of certain glass fibers, the elastic after effect is not small, it is longer. So the after effect is too long, so the effect is longer. Okay, so that means the glass fiber does not immediately come back to its original shape. Rather, it will take some time before it will regain its original shape. That is what we call as elastic after effect. Is that clear? Right? Now, what is elastic fatigue? Now, fatigue is a very common English word. You all know that, where fatigue is you are too tired, isn't it, children? So that's what happens with the elastic material also. If you are going to, subject the body to stress once, you are going to subject it to a strain, that means you're going to deform it once, the body will still, withstand the deforming force and regain its original shape. Lekin bar, if you're going to again and again, alternatively, you are going to apply stress, remove it, apply stress, remove it. When you are going to do it, the body is going to give up. The body is going to say, I am not able to withstand this. So what happens in that case is the body will give up and the body will break. That's what is going to happen in elastic fatigue. In elastic fatigue, what is going to happen? The body is going to break. When the body breaks, I'm going to show you a simple example here. You would have seen this in many cases. This is a simple wire that is being shown here, where a person is going to pick up this wire and he is going to apply stress on and off, on and off. Do you see here? He has picked up and he has bent it now. Once bent, he left it. It's going to go back to its original shape, if not fully, but a little bit. But see what the person is doing, children, now. The person is repeatedly applying and removing it. So at one point, the wire breaks. Now, again, he's doing the same thing with the next part of the wire. You can see that he's going to apply, remove. So all you are putting a stress, removing it in opposite directions, alternating it, and you see that the wire is broken. So that means the wire has lost its strength. The wire has lost its elastic strength, and the wire gives in. The wire no longer withstands the stress that is applied on it, and the wire breaks. So what is elastic fatigue? The loss in the elastic strength of a material, of any material. The loss in the elastic strength of a material. And why does it lose it? Caused due to the repeated application of stress on it. Right? Repeatedly, you keep applying, you remove it. You keep applying, you remove it. So you are going to repeatedly apply a stress on the body and alternate the strain and alternating strain. Right? So the loss in the elastic strength of a material. And why does it lose it? Because you are going to repeatedly apply stress and the alternating strain. That means stress causes a strain and then you stop it. Stress causes a strain and then you stop it. As you saw in the example that I projected to you as a video. And this is what this phenomenon, the loss in strength, is called as elastic fatigue. And this is called elastic fatigue. Now, because of this elastic fatigue, it is because of this reason that over usage, over years of usage, some of the bridges are, they say that it is unsafe to move on it. Though from outside you will see that the bridge is sound and safe, but the government or the state authority or the district authorities would have asked you not to use the bridge because of the unsafe nature which would happen due to the vehicle movement on the bridge. So this is what we call as elastic fatigue. Now, what is elastic hysteresis? I think I mentioned about this when we did the stress strain graph. When we did the stress strain graph, if I am going to take stress along the y-axis and strain along the x-axis, I'm going to take strain along, it's still fine, strain along the x-axis. If I'm going to keep on increasing the stress, let us assume that the body, it is not obeying Hooke's law. Let's say the body moved on like this. As I'm going to remove the stress, the body will not retrace its original path. Rather, it will follow a different path. So this is how you went up and this is how you are coming down by removing the stress. Such a loop is called as hysteresis loop. Please have a look at it carefully because next year we will be doing magnetic hysteresis. We are going to say that when a body is going to be magnetized and when the magnetizing external agent is going to be removed, it is not going to demagnetize in the same format. So here, when I'm going to apply stress, if it goes in this format, when I'm going to remove the stress, it is not going to retrace its path. It is going to come back in a different format. If you remember in our stress strain curve, we said something called as permanent set, if you remember. That's what we call as elastic hysteresis. The fact that the stress strain curve is not retraced, it is not going to be retraced on reversing the stress, is known as elastic hysteresis. Is that clear, children? On reversing it, that is what we call as elastic hysteresis. So these are the three elastic effects that we should remember. That is elastic after effect, elastic fatigue, and elastic hysteresis. Now we move into the applications of elasticity. Though we may not appreciate it now, after this session, children, I would very much like you to appreciate some of the structures that you see when you go around. Now, what are the applications of elasticity? The most important thing is about the elastic limit. Now, what is elastic limit, children? If you remember, the region in which the stress varies proportionally with strain. That's what we call as elastic limit, isn't it, children? And what is elastic strength, children? Ultimate stress. Do you remember we did all this in our stress strain curve? The maximum stress that a material could withstand without fracture is what we call as ultimate stress. If you remember from your stress strain graph, ultimate stress. Now, why am I talking about these ultimate stress? If any more, say, if you are going to look at a crane, you're going to look at rope cars, you are going to look at any rope, which is a metallic rope that is going to pull, hold, carry something. Please remember that the strength of the material of the wire is decided, the diameter of the wire is decided by taking into consideration the ultimate stress that the wire can withstand. Is that clear, children? So we are going to look at it. So let us assume that there is a crane that is going to lift like 10 ton of mass. Okay, so 10 ton is nothing but 10 into 10 cube kg. So that's around 10 power 4 kg. So what design people, engineers do is they will keep a cushion factor of 10. Cushion factor of 10 money, they will build the structure in such a way that it can withstand to a maximum of 10 power 5 kg. That means it is going to hold a weight of 10 power 4 only, but they will not give the cutoff as 10 power 4, but they will give a safety factor. We call that as safety factor, and this safety factor is always in the order of, is not always, mostly in cranes it's of the order of 10, let us say. So what will happen, the maximum weight that it can hold, the mass, will be 10 power 5 kg. So what is ultimate stress? Ultimate stress is going to be F by A. So what is this F by A going to be? Mass into gravity. So let me consider the gravity to be 10. So let us assume that the area of cross section of the wire is pi r square. This maximum stress, the ultimate stress, will be compared with that of the ultimate stress that is for the given material. So if I am going to take for steel, this value is equal to 30 into 10 power 7 Newton per meter square. So using this particular value, if you are going to calculate the radius of the wire, it will come to the order of approximately 3 centimeter. You can calculate it later. But if I am going to make a wire of thickness radius 3, that means diameter 6 centimeter, it will not look like a wire, rather it will look like a rod. Isn't it, children? So what they actually do, if you have a chance, please, if you have a chance to look at such wires, aage se, you will have a closer look at it. Even in building structures, you would have seen, it will not be a single wire, rather it will be it will be made into a thick rope that is made up of, a number of thin wires that are going to be braided together. So such a rope which is made up of thin ropes braided to bring this particular thickness, will allow it to, hold that particular weight. So if we are going to, say, look at it, I'm going to show you something over here, a crane. We are going to use this in crane. And nowadays we even have, bridges that are going to be held by ropes. Do you remember, children? Yes, I'm going to show you one particular, figure now, and I'm going to see if you are going to identify this particular place that I'm going to project on your screens now. So let me see if you identify this. Take a moment, pause it, and see if you identify which structure is this, children. Have you paused it? Have you thought about it? Yes, if you have got it right, this is our Lekhi Koi link bridge, right? Yes, children, so this is our bridge in Lagos. And do you see here, you have actually ropes, more than the pillars that you see the below here. You see the ropes that are going to hold the bridge. And next time when you are going to pass over here, please get down and appreciate the elasticity of these steel wires that are holding the stress applied by the traffic on this particular bridge. Is that clear? So that is one of the most beautiful applications of elasticity. So before they would have built it, they would have sat down to see what is the average stress that the bridge will undergo at a given period of time. So they will calculate it at a maximum. They will have a safety factor of 10, and then based on this, they are going to decide the thickness of these wires in order to hold the bridge intact for the safe travel on this bridge. Is that clear, children? Now we are going into another example of these wires. I'll show you one more example. You people would be more familiar with this particular picture on your screens. These are rope cars basically, and you would have gone in such rope cars, particularly when you go for your vacation outside India or in hilly regions, wherever you need to move. And you can see here, children, this is a photograph of the rope car in Hong Kong that takes you to a place called Ocean Park. Right now, if you see here, children, do you see the number of rope cars that are on this particular rope? You can see the amount of stress that the rope will be subjected to. And you should appreciate, again and again, I use this word appreciate, you should appreciate the engineers who would have put the safety of all these tourists in mind, and the amount of stress at one point of time these ropes will take in, and accordingly the material would have been chosen, the thickness of the wire would have been made, right? And that is where the elasticity of the material plays a very, very important role. It is a separate branch of study, children, please understand. Property of solids, mechanics, particularly mechanical properties of solids, is a separate area of study where the elastic property of the material is studied to be used in various walks of everyday life. Please understand, various walks of everyday life. Right, children? Now, I'm going to show you one more picture, and I'm going to ask you if you can identify this particular picture that I'm going to put on your screens. This, I think most of you would immediately identify. Yes, you can see this UBA building here. So immediately everybody will guess that this is our famous third mainland bridge. Right, children? So you can see it here. Do you see all these pillars? How many of you would have appreciated these pillars? How many of you would have tried to see why these pillars are made of such a shape? Now, from now on, you are going to see this. You are going to, look at the physics behind it, and you are definitely going to tell this to your parents and your brothers so that they also get to know the physics behind, the reason behind the shape of these bridges. These bridges are called as I-shaped cross-section bars. Now, why does this happen? Let us assume that I have a bridge that is going to be of rectangular cross-section like this. Let us assume this is the bridge that is going to stand on two edges like this. And if I'm going to move a heavy load over here, let us assume the bridge will bend here. It will bend like this, isn't it, children? Because the weight W is equal to mg is acting in this direction. So what will happen? The bridge bends. The bridge bends to such a depth. This depth is called del. And if I assume the length of the bridge to be L, the thickness to be D, and the width of the bridge to be B, right? And this bending is going to be inversely proportional to the Young's modulus of the material of the bridge. It looks so vague, but yes, an engineer should know this. So in order that he finds out, he reduces. This phenomenon is what we call as buckling. This is called as buckling, right? Buckling of the bridge. If the buckling becomes more, that means the bridge is going to undergo a crack. So what we do is, instead of having a straight shaped bridge, we use an I-shaped bridge. So when we, when we use an I-shaped bridge over here, this extra area, you know that stress is always inversely proportional to area. So the ultimate stress, because of the increase in the area, will reduce even for the same amount of vehicular movement on the bridge. I'm going to show you another video over here for you to see. Please have a look at it. Let's look at this video, children, where they are going to talk about what I said about the bridge. Let us assume a bridge over here, a beam here, that's going to be resting on two side pillars. Right, so we are going to take the length, breadth, and depth of the bridge like this. So what happens when the weight is applied? You see that it undergoes a bending, and that amount of bending is given by W L. Do you see, children? WL cube by 4y BD cube. Please, there is no necessity for you to remember this answer. It is only for your understanding that I'm putting it for you. It is inversely proportional to the Young's modulus. Is that clear, children? This del is what we are going to call as, right? So to reduce the bending, what we need to do is we need to use a material of larger Young's modulus. You can see it on your screen because it is inversely proportional to the Young's modulus. So what if because it is inversely proportional to D, if I'm going to increase D also, my del will reduce. But if I'm going to increase D, it is not going to help me as much as in changing the shape of the beam. Please, wherever you are going to go see constructions, pillars in houses, pillars that are going to be built to increase the height of the building, what it does, it reduces the ultimate stress. So what happens? The I-shape, we call them as girders. These I-shaped girders, they do not bend because you are going to have the structure made like this. Do you see? Have we appreciated this before? I'm using this word appreciate more number of times in this class because we fail to do that many a times, isn't it, children? So how many times while moving on a train, we have been talked about the pressure reduction due to the concrete bars. But today you come to know about the I-shaped cross-section of the railing also, which helps us to reduce the stress. So the stress is more reduced when we are going to use an I-shaped pillar. Do you see here, children? Even in household things, we are going to see, I-shaped pillars that are going to reduce the amount of stress that the structure can withstand, so that it is, it is going to be safe for a longer duration of time. So I have introduced you to two major real life applications of elasticity. One is the determining the radius of the rope, which is going to be used for load bearing, and the other one is the I-shaped bridges that is going to be used in order to build bridges, and not only bridges, also your huge structures that are going to hold a greater mass. Right, children? So this finishes off our first chapter, that is mechanical properties. These were our objectives, and I feel that we would have achieved these outcomes. Differentiate elastic after effect and fatigue. Understand the importance of eye-shaped cross-section of bridges. I've used my word once again. You would have become fatigued while listening to this word appreciate, but I do want you to appreciate not only the physics in your surroundings, but also some, few very good things that are happening around you even in these tough times. So learn to appreciate, and in the next class I will meet you with a new lesson. Till then, stay safe.